this video, we'll go through around 20 2D shader graph effects. We'll focus especially on two categories of effects: effects with Sprite custom lit shaders, where we can create unique effects by sampling the 2D light textures, and we'll cover effects that use the camera sorting layer texture for camera rendering based effects like glass refraction and distortion warping. Each effect has something unique and useful to learn from. Lots to cover here, so let's get to it. There's a package linked below with all the effects we'll cover, though you can certainly build as we go. If you do download the package, it's important that the layers are set up properly. I've imported the package into a blank 2D URP project and opened the scene in the project folder. If I look at this highlight star object, in layer it says unknown layer. To fix that, go to project settings, tags and layers, and then click on the little slider icon here. From there, click on tag manager. That way you can get all the layers intended for the project. Next, go into Settings in the 2D Render Data and set the foremost sorting layer to foreground. We'll go over this in more detail, we're just getting things working. And finally, in the Package Manager, import the Visual Effects Graph package. On my end, I'm not seeing anything different. All I needed to do is press play, and then things work outside of play mode. That should be enough to get everything working. For the tutorial, the approach will mostly be in the context of a blank project. Let's start with the basics of using light textures. By creating a Sprite custom lit shader, we can understand how the light textures are used in regular Sprite lit shaders. From there, we'll create an effect where we pixelate the lighting textures. First, I'll make a square sprite, have it fill up the whole screen, and then in the project folder, I'll make a Sprite custom lit shader graph. That's in shader graph, URP, Sprite custom lit shader graph. The Sprite custom lit graph gives us access to the 2D light texture, and we'll take a look at exactly what that is. So let's call this shader background underscore custom lit. I'll make a material of the same name, assign the shader to it, and drop it in the Sprite renderer. Click the shader and let's open up shader graph. In the graph, right-click and search for light texture. 2D light textures are render textures created by the 2D renderer that contain the visible lights in the scene. There are up to 4 textures representing each blend style in the 2D render data. Here's the 2D render data asset, and these are the default light blend styles that correspond to the 4 different light textures. The built-in lit shaders actually sample these textures and combine them with the sprite's textures to create the lighting effect. And that's exactly what we're going to do here. We need to sample this texture just like any other texture. Therefore, next, get a Sample Texture 2D node. We also need the screen position for the UV coordinates so that our lighting is mapped correctly to the object. The first blend style is for lighting that multiplies the colors, so therefore we need a Multiply node, and this group of nodes is the basic setup for adding 2D Multiply Blend Mode lighting to any shader we make from here. Let's group this up and call it Sample Light Texture. Now let's simply add a Vertex Color node, which will give us the colors and alpha from the mesh vertices. Basically, this gives us access to the color settings in the Sprite renderer. Let's hook this up to the multiply and save it, and then look at the scene. In the scene, create a Spotlight 2D that's in light, and not the Sprite light, but the Spotlight 2D, and we can see the light shining on the background. If you select the background object and change the color in the Sprite renderer, everything works as you normally expect it to. So we're not in total darkness. From here, make a global light 2D and bring the intensity down. We can see that the global light also contributes to the light texture. If you were to bypass the light sampling and switch the shader to Sprite lit, back in the scene, you won't see any difference. But if you hook things back up, we're still in Sprite lit, you'll get this error that says validation 2D texture node is not allowed by universal implementation. In Sprite lit, we're not allowed to sample the light texture because it's already happening behind the scenes in the Sprite lit shader. Let's switch back to Sprite custom lit and save it. The error doesn't actually go away, so to fix that, just delete the node and get the same node again, the 2D light texture node. Now that we have lighting in our scene, we can actually see the light texture in the preview. What can we do with this? Well, we can mess with the lighting in cool ways. As an example, let's pixelate the lighting. Let's save this shader as base_custom_lit, and then let's save another one and call it pixelate_lighting_custom_lit. I've turned off the global light. We're focusing on the spotlight. Let's delete the multiply and vertex color, and we'll start with the simplest node group. This will make more sense when the whole graph is together. This group is just a smooth step adjustment of our lighting. The float parameter called lightAdjust is a slider that clamps values to 1 above a threshold. Let's remap the values because the slider makes more sense inverted. Okay, and here's how the parameter looks in the graph inspector. It's set as a slider in mode. All right, so we'll save that. We're already affecting the shading of the sprite, which is why we're starting with this. Now let's do the pixelation. We want to pixelate the UVs. So let's move the graph over, add a parameter called pixel resolution, and make it a slider going from 1 to 200 or more. We'll use this to adjust how pixelated things are. This group here is our pixelation. Copy this and then I'll explain it. And there is a reason for the multiply here. We need to do some aspect ratio correction, but let's look at and understand the effect first. Here's a comparison and branch to visualize how the pixelation works. Let's just look at the Y or the green. UV and screen position values go from 0 to 1 in decimals. What we want is stepped decimals, like if we had 10 steps, like I have here in the pixel resolution parameter, we'd want 0.1, 0.2, 0.3, etc., with nothing in between. If we multiply by 10, our values go from 0 to 10. And then if we floor all those values, they're all rounded down. That means all of our values are now stepped 1, 2, 3, 4, 5. So our values currently go from 0 to 10. And we're using a less than here, so 10 actually will be the top. Then we want to take these stepped values back from 0 to 10 to 0 to 1. And we do that by dividing them by 10, the original pixel resolution number. Our end result then is 0.1 stepped increments. The pixel resolution can be any number of increments. 10 is just the easiest to understand how this all works. The 0.5 offset correction in the addition above is there because we don't want a value of 0.92, for example, to be to the top or off the grid. Let's do the aspect ratio correction, and then we'll come back and we'll look at this offset value. Bring the pixel resolution down to around 10. That way we can clearly see how each pixel isn't square, they're actually rectangles in the ratio of our screen, which is what we need to correct. Here's the aspect ratio correction group, and the math here is like how the 16:9 aspect ratio can also be expressed as 1.77 to 1. We want to multiply our pixel resolution by the aspect ratio correction, and then let's connect that up to the multiply for multiplying with the screen position. And since we're multiplying the correction in, that means we also need to divide by the same values later on in the pixelation group. And there's our lovely square pixels. Now let me put the resolution down to a good amount to where we can look at the little correction we have in the pixelate group. Let's get rid of this 0.5 addition and see how that affects things. All right, you see everything moved up and to the right. Now let's try it at 1. Now everything's down and to the left. So 0.5 keeps things centered. That may not seem like much, but if you're pixelating a sprite sheet for a flipbook animation, the sprites are really tight on the grid, so you want to keep things centered. Let's see how this lighting effect works on something in the scene. There's a link below to all these shaders and the assets we're using in this video. I'm bringing in the couch from our Happy Harvest project. It's all set up with the secondary textures. It needs to be scaled down, and then in the lighting, we need to enable the normal map. And then let's rename this game object to Pixelate Lighting. Let's put this in front of the couch by changing the order in the sprite renderer. Then go back into the shader to the Smooth Step Lighting Adjust group we did first, and also connect it up to the alpha. I'm going to make some adjustments to the spotlight, and then tweak the settings a little bit. Then I want to have that cone of light coming from the spotlight. For that, I'll make a square sprite for the background. Then I'll scale it up to cover the screen, and then we can put it behind the couch. There's lots to tweak here between the pixelated light object and the light. Here we're pixelating the lighting on an overlay and background object, but another approach we can take is to pixelate the lighting directly on a sprite. This variation is called Pixelate Sprite Lighting, and we're sampling the main texture, multiplying it with the pixelated lighting, and we're also sampling the normal map. We're not pixelating the sprite at all, we're just pixelating the sprite's lighting. The regular sprite lit shaders work great with pixel art. This is just an example for you to work with. We'll move on to camera sorting layer effects next, but if you're following along in a mostly blank project, you might want to have a simple background to warp or distort. And this gives us a chance to touch on a couple things. If you look up tutorials on shader graph effects, like here's a common one, a world height or position-based color gradient that lerps between two colors with a smooth step to adjust the transition smoothness. It's nice to have a background like this be lit with 2D lighting. To enable that, all you need to do is switch the shader from lit to sprite lit. Of course, you'll also want to use this material in a sprite renderer. Since we're using a sprite lit shader now, not only do we get the 2D lighting, we can also add in secondary texture details, like a normal map. In this case, we have a simple noise, aspect ratio corrected so it's not stretched if the sprite is scaled. The noise goes into a smooth step node into a normal from height node. The smooth step gives us a way to clamp the noise, which gives a concrete-like effect, like puck marks. And the nice thing about doing this procedurally is that there's no tiling whatsoever. If you bring the normal map way down, we get a paper-like surface, which we can blend with the normal map of any sprite. In this chapter, we're going to go a little further and use procedural patterns to make sprite-lit backgrounds. This is quite fun to tinker with and a great way to practice using the smooth step and blend nodes. And you can start with this gradient background where we already have some color parameters. Or if you want to experiment with the lighting textures, you can use a custom sprite-lit shader graph like the base one we made at the start of the video. To use all the procedural patterns, we have to import them first. So let's go do that. In the Package Manager window in Unity Registry or Packages in Project, go down to Shader Graph, and then from there, go to Samples. The first sample gives us some procedural patterns, and there's quite a few. Bacteria, bricks, dots, grids, and hexes, those are quite useful. And while you're here, you might want to grab the other two samples as well. Import the procedural patterns, and then back in the shader, you can find them in Patterns, Complex, and Simple. And then in Procedural, there's the checkerboard. So pick any pattern you like. I'm going to pick bacteria, and let's add some colors to them. So first, I'll categorize away the gradient parameters, and then add a color A and a color B, because from here, things are more open-ended, and you're going to have something different from what I have. If you haven't yet, save this shader as pattern background. Each pattern is different, of course, but these two groups should help you add color. We're using a blend node in overwrite mode to blend the two colors together. If you're using a sprite custom lit setup, you'll multiply this with the light texture to get the same result as a sprite lit shader. The bacteria is fuzzy, which is actually a good thing because we can use the grayscale values to make fills or outlines, but first, before that, to sharpen up the pattern, we use a smooth step node with a subtract node and a slider parameter called sharpness going from 0 to 1. This is the same smooth step setup as the position-based color gradient smoothness. We're just flipping the parameter for sharpness instead. This fuzzy blurriness is called a distance field, which we can use to make sharp graphics without the need for large image textures. We can use another smooth step to mask in a fill color. The fill threshold acts on the gradual grayscale values of the shape. And I have a remap so that the slider is more intuitive. Let me hook that up so we can actually take a look at it. Turning the fill threshold all the way down, there's no fill, we just get color B. Now everything in the pattern that is around 0.99 something is made 1. And as we turn this up, we clip lower and lower values to white, which means more of the shape gets masked in until every value above 0 in the minimum is white. This is similar to what we did with the concrete noise. And if that's confusing, you can do the same thing with a comparison node, bacteria as the minimum, threshold as the maximum, and then grayscale values greater than an amount will be clipped to 1, and everything else will be 0. All right, hopefully you didn't mind this tangent. Let's continue on with the second main category of effects, using the camera sorting layer texture. The camera sorting layer texture is the rendered output of all the sprites on a sorting layer. We can use this render texture for all kinds of different effects. We'll start simple with color-based effects and then move on to distortion, warping effects, as with glass, heat haze, and ripples. Using the texture in the shader graph involves simply having an unexposed texture parameter called _camera sorting layer texture and sampling it like we did with the light texture. But before we get into shader graph, we have a little setup. I just wanted to show you where we're going. Go to the project settings in the tags and layers. And in sorting layers, we have the sprite sorting layers. Mine here are from the Lost Crypt project because these are the kind of layers that you'll have in a game. Make a special layer for the camera sorting texture. I'm calling mine CSLT effects. And then in the render 2D data asset, go down to camera sorting layer texture, hover over the foremost sorting layer here, and it says layers from the backmost to the selected bounds will be rendered to the camera sorting layer texture. I'm going to put this to the layer right before the CSLT effects layer, meaning that all the layers but the CSLT effects layer will be in the render texture. Okay, now you can make a sprite unlit shader graph. It's important it's unlit, and call it CSLT highlight. We're just going to get something simple working, a highlight effect with a multiply node. If you're following along, copy what I have here, a 2D texture _ camera sorting layer texture that's unexposed. Bring it in, sample it, connect it with the screen position to UV input, and then get a multiply node. Create a sprite and pick a sprite for your highlight. I'm using a rounded star sprite. Drag in a material that has the highlight shader, and then this sprite needs to be on the CSLT effects layer. Your background can be on default. The parameters for the shader graph are the main text, a pulse speed float to adjust the frequency of the sine wave, and a min-max highlight vector 2 for us to adjust the remapping of the sine wave's amplitude values. We multiply in the color from the base sprite if we want to use it, and finally multiply with the camera sorting layer texture. So when the minimum is 1 in the min-max highlight vector 2, we shouldn't see anything different because we're multiplying the render texture by 1, and the sprite is white, which means it's 1. The render texture is then unchanged. If yours is dark on 1, check the layer setup and check whether the material on the shader is a sprite unlit. And you might want to make a volume with bloom and turn on post-processing in the camera for this. This is, of course, the same effect as using a sprite light 2D, but the nice thing about this is you can animate it in the shader like we're doing. And you have the shader graph to work with and refine the effect. Multiply is really nice for a highlight because you can see what's being highlighted, and the multiplication boosts the colors in the game world. Contrast that with addition, or simple transparency. The lower star is the same graph with the multiply swapped for an addition node. Addition, or a simple transparency, feels like an overlay that obscures what's being highlighted. Another benefit to having this highlight effect as a shader is that we can use it in a visual effects graph. Go to the package manager in the Unity registry and get the visual effects graph package. Then in your CSLT highlight shader, bring up the graph inspector. In graph settings, scroll to the bottom and enable support VFX Graph. Right-click in your project and go to Create, Visual Effects Graph. And call this Stars VFX, or something like that. Then drag it into your hierarchy. Just like with the highlight object, set the effects to the CSLT effects layer. Go to the component and click Edit. And then in the VFX graph, in the output particle quad, you may see a spot to drag in the shader. If not, go to Preferences and Visual Effects and enable Experimental Operators blocks. You could search for the shader you want, or expand it in the project folder and bring the shader in. From there, we see the shader parameters, including the main text. So let's make a parameter for that, just like with shader graph. That way we can easily change the particle texture on the VFX component. So add a texture 2D parameter, and I'll call it VFX main text. Hook the VFX texture up to the main text of the shader, and then expand the parameter in the blackboard, and let's find the star texture. Now we can adjust the highlight shader parameters. And what you can do then is pull out on one of these parameters, like the pulse speed, and then search for random to get a random number node, and then set a random range. And now the stars are more unique. So we have the effect of dozens, even hundreds of sprite lights, and we're pulling it off with shaders. There's a lot of cool possibilities here. In case you want to change the color, if you tried to change the color like with the set color over life gradient, so I'll just pick one that I have, you'll notice that there's no change because there's no color changing on the shader. I would suggest just using the alpha of the texture and then making a color parameter in the shader, which is multiplied with the sine wave. Save that, and then in the VFX graph, you can do a get attribute color, which will set the color on the shader from VFX graph. So I just dragged out from that new color parameter and search for get attribute color right there. And then you can do your typical particle color tricks. So this could be really cool for impact type effects where you don't want to obscure important aspects of the gameplay. So yeah, this can be a power-up or an impact effect where you can see the graphics behind. And now that you're hypnotized, check out this other one where the texture is a bunch of these little fragments. So this is really busy, but the important shapes and graphics of our scene are still legible. That's all for this one. Catch us in part 2 where we start out with a 2D glass shader.